Today we are going to study another shortest path algorithm using negative weight edges. So far we have studied Dijkstra's algorithm, which also calculates shortest path, but not in presence of negative weight edges. So today's algorithm is called BellmanFord algorithm. So let's see one more time. BellmanFord algorithm, what does it do? It solves the single source shortest path problem. Okay, this is very important. Remember it, that it solves the single source. I don't think it's visible. Let's use this one. Single source shortest path problem. Okay, in the general case, this is a general case, not like Dijkstra that there cannot be any negative weight edges, in which edge weights may be negative. Okay, this is negative. So now the problem definition starts from here. Given a weighted directed graph, we know this much from Dijkstra, with source S and weight function W e to R, where R is a set of real numbers, we know that, and every edge matches to a real number, whichever is its weight. The BF algorithm returns a Boolean value indicating whether or not there is a negative weight cycle. That is negative weight cycle. So first it finds out if there is a negative weight cycle or not. That is reachable from the source. Okay. So if such a cycle exists, the BellmanFord algorithm indicates that no solution exists. So no solution if a cycle exists. Okay. If a cycle exists, then no solution. No solution. And otherwise it produces the shortest path. So that means if no such negative weight cycle reachable from S, then only you can find the shortest path. This is very important point, okay? And also give their weight. Okay, so what does it do? It initializes single source shortest path. As I said, S is the starting vertex, S is in zero distance estimate, and all other vertices are infinity distance estimate for I equal to 1 to G dot V minus 1. So what is G dot V minus 1? G dot V is basically, here you can, just forget the G maybe, and just V minus 1. From I equal to 1 to V minus 1, okay? For each edge UV belonging to G dot E instead of G dot E, just say E, just for the sake of simplicity. That means each edge belongs to the set of edges. G dot E means that edges of the graph G, but we already have the graph G as the input, so just forget those things. Now relax UVW, okay? U is the starting vertex, V is the ending vertex, and W is the weight of that edge. So relax that edge. You remember the relaxations condition, right? So now you see, for each edge UV belonging to, again, G dot E, just forget this and just have E itself. If V dot D greater than U dot D, that means the V's distance estimate is greater than, V's current distance estimate is greater than the U's current distance estimate plus the edge weight connecting U and V. Okay, so relaxations condition, then return false. Otherwise, you just return true. So this part is checking, is there any negative edge weight cycle reachable from check for negative edge cycle. Okay, so this, if there is a negative edge cycle, if no negative edge cycle, then you return false. Otherwise, you return true. I'm not going too much deep into that because it needs some kind of proof to show that this algorithm works and can detect negative edge weight cycle. Instead, I will just show you with some example that yes, this kind of thing works. Okay, so yeah, so just see this here. This part you can see it is working for mod V minus 1 time, okay? So this, you see this loop, for loop here. This is working for mod V minus 1 time. Just assume it's mod V times. And then within that, for each edge, we relax it, okay? So V times it's actually mod V minus 1 times, but when you do the complexity analysis, you will consider mod V times. And for within that, for each edge, okay, so this is basically I mean, this for loop is for mod E times, and this is for mod V times. So the complexity of Bellman-Ford algorithm is theta of mod V times mod E. I hope you are understanding this. This is very simple, okay? So this is the basic idea of the concept of Bellman-Ford algorithm and the pseudocode. Okay, now we'll go for some example.